Hello AP Physics 1 students, so make sure you have your magnetism concepts page in front of you, and you're going to go right ahead to look at problem number 1 here, follow the instructions, pause the video, go through all these situations, then come back. So clearly we're playing around here with right-hand rule for forces. So is that the pointing one or the grabbing one? That's the pointing one. Okay, so if at any point in problem number 1 here you're doing anything with grabbing, pause the video, you're doing it incorrectly, try it again. Okay, so for letter A here, what we're looking at a positive point charge, and here's the velocity vector pointing into the page. If you're confused about that, pause the video and try it again. Alright, so we start with our right hand, our pointer fingers pointing into the page. We twist our wrist until we can comfortably curl our fingers to the right for the magnetic field, and we stick our thumb out, and that's pointing to the bottom of the page. Alright, let's take a look at letter B. Here we have a negative point charge, it's moving to the left, and we have the magnetic field pointing to the bottom of the page. Right, so we do that, and we have our thumb pointing out of the page. But oh, wait a second, hopefully you caught the trick here. It's a negative charge. Remember, that's the only trick. That's pretty much the only trick you can play here with right-hand rule is the wrong sort of charge. So what do? Well, we just flip our answer. So if our thumb is pointing out of the page, then we have our magnetic force pointing into the page. Alternatively, you can say a negative charge moving to the left is like a positive charge moving to the right. So why don't you try that? So now our fingers are pointing to the right, and this is kind of uncomfortable, but you should curl your fingers to the bottom of the page, and now your thumb is pointing into the page. And remember, if that's uncomfortable, you want to try that, you can always turn your paper around any way you want to, so it's a more comfortable situation for you. Right? So you can either flip your answer, you can flip the direction of velocity, or of course you could use the other hand. I don't like using the other hand. I always want to use my right hand, but it does work. I just strongly advise you don't do that. However, remember, if instead of saying into or out of the page, you're still saying your thumb is pointing up or down, you've got to stop that. Right? You've got to get that out of your vocabulary. Unless we definitely know we're looking from the side, we really shouldn't be using the words up or down. It should be into the page or out of the page for situations like that. All right, letter C, what are we looking at here? Hopefully you recognize this is a wire with current, and this X here represents the flow of positive charge. If you didn't get that, pause the video, come back. Okay, so our fingers are pointing into the page, the flow of positive charge, and then we twist our wrist until our magnetic field is pointing to the top of the page, so we curl our fingers to the top of the page, and then our thumb is pointing to the right. If instead you were grabbing the wire, still confused about that, you've got to go back and review which right-hand rule is for which. I was very specific about that, right? You should not be grabbing that wire. It is sitting in someone else's field. This is a force problem. This is a pointing right-hand rule. And the magnetic force is pointing to the right. This whole wire feels a force to the right. For letter D here, if you were confused, this is a loop of wire, and the charges are moving around this way in a clockwise direction. We're not showing the voltage source. It's sort of imaginary. It's there, but it would sort of muddy up the picture. So just imagine there's a voltage source here, and you should be grabbing you should be pointing for individual sections of the wire. You shouldn't be grabbing anything. This is not the right-hand rule shortcut. So if you were confused about that, pause the video, try it again. Okay, so I'm going to start here on the left side. We see the charges moving to the top of the page. The magnetic field, all those X's are pointing into the page, and so that left-hand side of the wire is feeling a magnetic force to the left. And then we get the top part of the wire. We just sort of trace those charges around. You see the charges moving to the right in the top part of the wire. The magnetic field is into the page, and so the magnetic force on the top section is to the top of the page. And then on the right-hand side, just trace those charges. It's now moving to the bottom of the page. Magnetic field into the page, and so our thumb is pointing to the right of the page. And just trace those charges around. Now they're moving to the left to complete the circuit, and the charges moving to the left, fields into the page. The magnetic force on this section is to the bottom of the page. But read the instructions carefully. It asks for the net magnetic force. And since this is a rectangular loop of wire, which means the left side length is equal to the right side length, the top side length is equal to the bottom side length, and magnetic force is I LB sine theta. Since the currents are all the same and these opposite side lengths are the same, this magnetic force is equal to this one, this magnetic force is equal to this one, all these forces cancel, and the net magnetic force is 0. What really happens, well, if this is some sort of flexible piece of wire, and all of a sudden we turn the current on, these forces tend to try to sort of expand the wire, and it may reshape the wire, but in the end, the net magnetic force is 0. On to letter E, in a similar fashion, we're going to trace the charges around, but now the magnetic field is pointing to the top of the page. On this left-hand side, the charge is moving to the top of the page. The field is also to the top of the page. What's the magnetic force? Well, it's 0. Right? Remember, anytime charges move with the field, they don't experience magnetic force. They have to somehow cross magnetic field lines. Or what angle would this be? This would be an angle of 0 degrees. The charge is moving in the same direction of the field. That's angle 0. Sine of 0 is 0. And so there's no magnetic force on the left-hand side. What about on the top section? The charge is moving to the right, feels to the top of the page, and our thumb is pointing out of the page. So the top section feels the force out of the page. How about in the right section? Now the charge is moving to the bottom of the page, feels at the top of the page. Well, we know what happens. There's no magnetic force. The angle is 180, sine of 180 is 0, or again, anytime charge is moving directly against the field, they feel no magnetic force. On the bottom section, charge is moving to the left, feels at the top of the page. The bottom section will feel a magnetic force into the page, but these two sides of the wire are of equal length. These two magnetic forces are equal and opposite. The net magnetic force, once again, is 0. Okay, so now go ahead to problem number 2. We're looking at these different objects here. What are these we're looking at? These are electromagnets or solenoids. Here we do see the source of voltage and the wires wrapped around. And so go ahead and try letter A on your own, then come back to see how I do it. I want you to just try letter A, just in case you're not quite sure how to do it, and then you'll go on to letter B and C afterwards. Okay, so I'd shown you in the previous video how to do this. First thing you want to do is trace the charges. So we have the long side of the battery shown here, and we know that's the positive terminal, and we do conventional current, charges are flowing out of the positive terminal, and then the wire loops around the back of the core, and so you should be able to see that any time we're in the front sections of these wires, the charges are moving to the right, around the back, to the right, to the back, to the right, around the back, to the right, and then completing the circuit. This is the first step, which way the charge is moving. We're now finding a magnetic field. So here is yes, we're going to be grabbing wires, or you could do the right-hand rule shortcut. I'll go through both. The grabbing the wire one is I would grab one of these sections of the wire that is close to us, and our thumb is pointing to the right, and then we wrap our fingers around. Now here, all we care about is the magnetic field in the core, in the interior of the solenoid. That's where all the field lines are bunched together, and we have a pretty much uniform field inside. And we should see that when we stop our fingers, they're pointing to the top of the page. Alternatively, you could do your right-hand rule shortcut. Here's where we do basically the exact opposite. Our fingers follow the charges, so now our fingers are pointing to the right because we want to see the charges where we can see them in the close part of the wire. And then you just sort of follow your fingers, and their thumb should be pointing to the top of the page. No matter how we do it, our magnetic field inside the solenoid is to the top of the page. Just remember, when you do the right-hand rule shortcut, your thumb is showing the direction of the field in the interior of the wire, the area bounded by the wire. And that's all we care about. Okay, so now go ahead and try letters B and C, following again the right-hand rule shortcut or grabbing the wire. Letter B, hopefully you notice that while the voltage source is pointing the same way, oriented the same way, now the wire loops the other way, right? So now the wire passes in front of the core in front and then behind, and so as we trace our charges, now they're moving to the left in these near sections of the wire. So either grabbing the wire or doing the right-hand rule shortcut, you should see the magnetic field in the interior of the solenoid pointing to the bottom of the page. Making sure we're not just, doing everything again, not trying to reinvent the wheel every single time. Letter C, you should notice that now the wires are looped around the same way as letter B, but now the voltage source is flipped, and so something has changed, and so now the charge is moving to the right. And again, you could grab the wire or do the right-hand rule shortcut, but not reinventing the wheel. You should just see that anytime the charge is moving to the right in the front part of the solenoid, well, it's basically going to be this same situation, and so now the magnetic field lines point to the top of the page. And while this is approximating the same thing as a bar magnet, if you had drawn some magnetic field lines looping around the outside to show the bar magnetic field pattern, that's a good idea too. But really, all we really care about are the magnetic field lines in the interior of the solenoid where they're bunched together. The last step here, even though it doesn't say so, is to identify the north and south poles of these electromagnets. So pause the video and go ahead and do that. So following our rules, magnetic field lines come out of north poles and go into south poles, and so for letter A, this is the end where magnetic fields are coming out. For letter B, this is the end where magnetic fields are coming out. This is the letter C, magnetic fields are coming out. And wherever magnetic field lines come out, those are the north poles. This would act as the north pole, this is the south pole. Over here's the north pole, this is the south pole. And since letter C is the same as A, the north pole is on the top edge, and this part towards the top of the page, and south is the edge towards the bottom of the page. Okay, we're going to continue here in our problem set with problem number 10. So go ahead and read that. We're doing some Faraday's law, some things that we change about flux. Let's go ahead and try parts A and B and then come back to see how I solve it. Okay, so how do we know we're doing Faraday's law, even though I did just tell you? Well, something is changing. In this case, the interior loops of wire are being rotated in letter A. Excuse me, the magnetic field in the outside solenoid is being changed. Letter B is the one that's rotating. And so what we're looking at is here are the loops of wire, sort of stacked loops of wire. This outside section, that's the solenoid. I'm not showing the loops of wire there. That would just sort of muddy up the picture. But the outside field is changing, which will then change the field in the interior. That's going to induce an EMF in these loops of wire. So it's negative N delta phi over delta T. Remember, phi is the magnetic flux. sort of measure how many field lines are passing through the loop here, and this is the average induced EMF. It does ask for magnitude, so we can go right ahead and put absolute value bars around this. We're not going to worry about the signs on anything. And what I like to do is I like to replace flux with its equation, BA cosine theta, really spelling out what is it that's changing. Alright, so the problem talks about the area or the dimensions of the loop, and that's not changing, and the orientation is not changing, so I'm going to pull those to the outside. So this is capital N, that's the number of loops, this is the area, and cosine theta is not changing, but what is changing is the magnetic field in the outside solenoid. So I just sort of group together things that are constant and then group together things that are changing. And then you might say, well, we need to find the change of magnetic field, but that's not true because the problem flat out tells you the change of magnetic field with respect to time is 0.4 Tesla per second. So that is delta B over delta T. They tell you that the normal of the loop makes the same angle, the angle of 0 degrees with the plane of the solenoid, and so that angle is 0 degrees. So just go ahead and put your numbers in, and you should have no problem getting 2.40 volts. Hopefully you recognize, of course, the dimensions of the loop are given in centimeters, so make sure you convert ahead of time when you find the area. And they're rectangular cross-section, so it's just length times width. All right, letter B. Again, we're doing Faraday's law. Again, we're going to take absolute value because it says magnitude. And what's changing this time? Well, it's going to be a constant magnetic field, held constant, and it's a constant area. What is changing is the angle. We are rotating the loop. And so I'm going to pull all these constants to the outside and just leave the thing inside that's changing. It's a change in cosine theta. This one's for all the sports fans. Oh, I know, we're all sad there's no sports right now. Okay, now here's a matter of, do you understand how this equation works? So is this the cosine of delta theta, or is this the change in cosine theta? They're not the same thing. If you're not sure about that, you should be able to prove that to yourself. But when this says delta cosine theta, that is the change in the quantity cosine theta. In fact, you're actually not going to get the same thing if you do cosine of delta theta. That's not the same thing at all. So we really should split that up. Any delta is final minus initial. So this is cosine theta final minus cosine theta initial. And if you didn't do that, pause the video and try it now, because that is an important distinction. And as always, make sure your calculator is in degree mode because the angles are given in degrees. We'll make sure we're doing cosine of theta final minus cosine theta initial, although honestly, since we're taking absolute value, we're not going to really worry about the difference there, but you know, we should always preserve the order final minus initial, and yes, we do take absolute value in the end, and so in the end we should be getting 1.05 volts. If you're not getting that, try it again, make sure you can get 1.05 volts.